Mm.
Uh, Welcome back. I'll allow the mic of all the students. I've allowed the mic and let me start. Just wait. I'm sure you would be able to see my screen. You can hear me now? Anyone?
Yes, sir.
Yeah, perfect. So we'll just quickly go what exactly we did last session, and then we'll come to what we wanted to do today, right? We were doing a classification actually, right? Just let me, yeah. So we started with classification. I'll quickly wrap this, right? So we talked about the definition, all those part. We talked about the examples. We talked about actually we were covering binary classification, right? So we talked about the definition and everyone knows about it before also. So then why not use linear regression? Because actually we would be doing, we started with something called logistic regression. So why linear regression is not enough? We discussed that thought process, isn't it? So we took this kind of example as well, if you remember. And why not linear regression would be enough for a binary classification thought process? We discussed it quite thoroughly, right? Uh, then we started with something called logistic regression, the classification module for binary classification, and we discussed the role of uh, this function as well, right? Sigmoid function. So the entire linear model gets embedded into the sigmoid function, right? Then we took a little bit of this thought processes. We talked about the sigmoid function, its derivative, what's the advantage of it, right? What exactly this is. We also interpreted the bell curve, right? Little bit of mathematics behind it. We talked about sigmoid function. We all know about it, right? We talked about this. We started with logistic regression. We modeled the logistic regression function using a single neuron model. That's what we started with, isn't it? And we the how the single neuron model. This is a perfect example of a single neuron model, right? And how we can project or how we model the logistic regression classification. We talked about this, right? I took this particular example in front of you, then showed you all the steps. So this would help you. I forgot to put this PPT, so I'll put this PPT today, right? I've modified this PPT quite a bit. So all these steps I have already told you that how exactly it happens, how the entire logistic regression happens. I've added this particular PPT which shows you if you just have missed out something, right? So what I've done is I've taken a simple problem statement where a single feature has been involved, right? And this is a typical data I have used for calculations. Hours of studied. I wanted to get, I wanted to analyze on the features of hours studied and right. And then the pass or fail are the two classes that we were talking about, right? So these are two classes. So the initialization of parameter happens, everyone knows it. So I'm trying to model it with a single neuron model, right? If you remember. So what we did is, as you know, I mean, the first, because there's a neuron that would receive all its input in the form of the X input, right? And everyone knows about W and B. So by assuming certain values of B and W and the given input, just a sample input, we calculated Z, right? And so what does it interpret as? you must know. So then we applied the sigmoid function as well. So giving it suppose zero point 0.5, and what's the interpretation of it? You understand it. So model predicts what? 50% probability of pass, right? And 50% probability of fail as well. So then we computed the logistic regression using the binary cross entropy loss. I also explained why a simple MSE would fail. In fact, I've explained that further as well, right? So we put this, substitute the values and all those. I think you should be able to do it very nicely. You came up with a loss. So what is the interpretation of this loss is that the model prediction is not very good. 69% is, loss is quite a big one, right? So obviously the model needs a training. Had their loss been, suppose, 1%, 2%, so even a person might think that there's no point of training as well. So that thought process should also be there, right? Then we started with the gradients, right? We computed the gradient. I hope everyone knows it. So when we use binary cross entropy loss, right? So this is what we are left with. We explained it before also, right? We substitute these values, we computed the gradient bias and everything, okay? And then the interpretation of gradient means what? So obviously, if it is negative, then I have to increase the parameters to adjust it well, right? Because I need to go in a direction where I can minimize that loss, isn't it? So if in case the gradient comes negative, so this is the action that is required. If the positive, then this is the action that is required, right? So obviously here the loss, you can see what kind of gradient that we have obtained, right? So gradient rule has been applied later on as a step. Then I've just taken one sample value of learning rate, for example. Then we updated the weights, updated the bias. So that is what we got it, right? So again, we would apply the forward bias to see what has happened to the learning, right? To the parameters and to the actual weights. So we obtained this next iteration. So after applying the new prediction and everything, we got this, right? So new loss computed like this. So new prediction interpretation is before it was suppose zero point 0.5. So after one learning step, it is this, right? So the prediction moves closer to the actual value, right? Isn't it? So learning is happening. So that is what we wanted to understand because initially before training, this was the case, and this is the loss right now. So this gives you interpretation, and this, I mean, you can extend it if you have programmed it. So you can see the loss is decreasing. Then I have already told you that you have to control the convergence part as a programmer, right? Either you can define that the loss should be within this particular range, or either you define the number of iterations, right? That is something that we have to do. So then I also explained about that why squared error of classification will not work. I hope my voice is coming. Hmm?
Yes, sir.
Yes or no? Yeah.
Yep.
Yes,
So
sir.
we talked about the concept of convex and non-convex as well, because I just wanted to make you aware that what exactly, because we really wanted to understand why not square error is enough for classification purpose. I'm talking about why not MSE, that mean square error that we used to do, that we used to use in the linear classification. Why cannot be it could be a fit for a classification method, right? So convex method function is, I told you, it has a one global minima. Non-convex, I told you, it has multiple values, multiple local flat regions, and all those things. So MSC alone was convex because if you remember in that regression, we look for the best value. It has a quadratic ball shape, right? So obviously, I would be looking for the minimum value somewhere, right? So it was possible. So it was easy to optimize it, right? When it comes to logistic regression, it actually is adding something called sigmoid. Yeah, everyone knows it. So we are adding this concept of sigmoid, and that is where it creates the problem actually, right? So the MSC now becomes like this, right? If I say so here, this is little different because one input and anyway. So if you see the entire thought process, I've given this example also in the previous session. So I took this value, I took W0, I trained on these three cases, right? So what I got is that when it was -10, So it gave me a very high loss, right? When it was this, it gave me this loss, and when W was 5, it gave me this. So, so it clearly shows that the log decreases very slowly at extremes, right? So this is an issue, and it faster near the center, right? So this creates a kind of irregular curvature. What I needed is a global for global minimization. I needed a kind of ball-shaped curve, right? Which I'm not able to get it. So it becomes a little bit of non-convex in nature. So the flat regions are definitely dangerous. I've explained that also. So the gradient actually descent barely moves even though the prediction is terrible. So I gave this particular example. I gave this thought process also. So when you use linear regression plus MSE, you might see like this. It is just a reverse, whether you talk about this or this way, right? So we have a very nice curvature and it becomes, the second derivative works, it's not required because it would give you a constant value, right? So when we talk about MSE plus sigmoid, I've explained this slide before also. I'm just pushing it up because I have to cover rest of the session as well. So when we talk about MSE and sigmoid, so we get these kind of flattened regions, which is not suitable to get a global minimum. And what is the role of a second derivative? Like second derivative tells you about it is actually tells the optimizer that how sharply should I move, isn't it? It's not the direction only. The first derivative would only give you the direction, but how sharply should I move? I need the second derivative also. So when it is a complex kind of ball, the second derivative gives you constant and becomes a stable movement. But when it talk about MSC plus sigmoid, so the it changes very dramatically. Sometimes in a positive direction, sometimes a negative direction, right? So so it is large in some regions, tiny in some others. So it gives you inconsistent curvature, right? And that is not suitable for the optimization part, right? And why we are talking of second derivative? I've just given you thought process. Why? Because which direction to move is not enough. I have need to also understand that how fast or sharply should we move. So that is only given by the second derivative thought process. Okay. So I've just given a thought process. Obviously you might get confused that why we're talking of second derivative. So you just given an example, edit this particular slide, that what we mean by first derivative. So what happens in the first derivative, right? And then we also need how the curve is curved is this particular surface is, and therefore I need a second derivative, right? So how rapidly the slope changes, whether the surface is smooth or flat. So these answers are given by the second derivative. So just a thought process for you all, right? So I also talked about this particular slide, that problem with what is the problem with the sigmoid derivative. I gave this particular analogy also, if you remember, that imagine a student who scores 1 out of 100 in the exams and teacher still says that only improve zero point 0.1 marks next time. So this is not realistic, right? It doesn't make any sense. So just go through this. I just wanted to come to what I wanted, right? So I gave this thought process also, right? So the idea was, um, if you see why gradient descent suffers, uh, because the gradient descent updates on the depends on the slope, and the slope is zero, then the updates become tiny. So that was the issue. By cross entropy avoids this. The derivative actually becomes this particular factor. So there's no multiplying by sigmoid. So the absence of sigmoid derivative is something which helps us when we talk about cross entropy, right? So how this cross entropy fixes this? So this particular equation is the only error remains in this form only, and that is a good thing. So and with I've just explained with the example also, right? So more about it and all those. So why cross entropy loss is better than gradient descent? I gave an example. I promised that I'll give you an example also, right? So I've computed one given example, right? So just to give you a thought process, for example, this is the first when you apply a sigmoid, you get suppose this particular value, which is nothing but the 0.5 probability of the pass. So a huge mistake has been done, right? Because the actual answer is one, obviously, right? So the model is confidently wrong. So when we talk about MSC, it would have done this way. It has created a huge loss. Then I have applied MSC plus sigmoid over here. So this is the term which is the issue, this particular term actually creates the entire problem, right? So you compute the sigmoid derivative, you get this. So very small value. Then you compute the full gradient, you get this. So what is the observation? Although the prediction is terrible, it was a very terrible prediction over here, but the gradient becomes only this. So obviously, if the prediction was terrible, then we expected that a huge adjustment should have been done from the gradient side, right? Which was not done. So this is because of this particular term, right? So what is happening to the learning? The gradient descent update, you can see it is almost no change, right? Earlier this value we can see from the data. So there's almost no change in the gradient descent. So that's the issue. So problem made a huge mistake, but the learner is extremely weak because the sigmoid derivative becomes tiny. And because the sigmoid saturated near zero, this shrinks the gradient. So this is the issue. But when you switch over to the binary cross entropy, so you get this kind of equation, right? And when you simplify the loss and all those substitute these values, so you get over here with the same example, very large loss, which is significantly correct, right? Because correctly punishing the confident wrong prediction. So when there's a wrong prediction, I need a suitable adjustment. है ना? So I took it with the cross entropy gradient this time now from for the binary cross entropy, right? And you see, you compute the gradient. See, so with MSE sigmoid, you get this. With cross entropy, you get this. So weight updates, and when you do a big weight update, so here you have done a good correction, a big correction. So cross entropy says so you were confidently wrong and correct aggressively, which was not possible or which was not seen in the previous example. So this is was the exact behavior I wanted, right? You'll go through it, you'll understand it. I'm rushing it up little because this is all we did previously. So it became little lengthier, I suppose. है ना? So you can have just summed up what exactly why MSE fails here because of this particular term, right? So, but sigmoid derivative becomes very tiny at extremes. So it's a huge mistake produced tiny learning. And why cross entropy is better? Because it avoids multiplying by sigmoid derivative, this one, right? And the wrong prediction gets a larger gradient and the strong updates and faster learning. Okay. So we also talked about the stochastic gradient descent and all those. I'm just rushing it up, right? So this is what we wanted to do. So there are certain metrics for classification that we'll do. And I have I've put my slides in a more detailed fashion so that everyone can understand it because this is also an important thought process and you might get certain questions from these metrics as well, for sure. So confusion matrix, I think everyone is aware of if you're done doing the machine learning, right? So one of the most important evaluation tool when it comes to classification problems, right? So what it does help you. So how well a classification model is performing, right? So this is something which it would be able to answer. So instead of just giving you the accuracy everyone knows how to be calculated, right? So accuracy may not be enough. So it helps us to not only get the accuracy but also how the classification model is performing. So that thought process, which predictions were right, which predictions were wrong, what type of mistakes the model is making. So we would be able to answer all these questions with the confusion matrix, right? So this is a typical form of matrix when it comes to binary classification. You would be able to see these kind of four quadrant approach when it comes to binary classification. So you have listed on one side the predicted values, on the other side you have listed what the actual values. This can be flipped also, right? So it is actual value versus the predicted values. So among the actual values, you can be positive, you can be negative. Similarly, among the predicted values, you can be positive, you can be negative. So, and based on this thought process, this becomes the true positive, this particular quadrant. So, true positive, I've given you an example also for a true positive. So, this is a quadrant of true positive. So, that's the reason I told you. So, if you flip this particular diagram, so this diagram and this diagram is flipped actually, right? Because I've put negative and positive. Here I've put positive and negative. So, therefore, the true positive section is this one, right? So, true positive says what? So, we predicted positive and actual was also positive only. So, both the things, the predicted and the actual was same. that it was the positive one. So in this image, if we predicted the woman is pregnant, she was actually pregnant, right? Right. So similarly, there would be another ideal cases would be true negative, right? So over here, this is a true negative case. So I predicted negative and it was actually negative. So obviously the man is not pregnant and it was actually not pregnant also, right? So two cases. I hope everyone understands it. Prediction, when you apply a model, so there would be some kind of prediction and there would be a corresponding actual value associated with this. So other than these are the two ideal cases, there can be two other cases which can be a flip, I mean, which can be different from what is prediction and what is actual. So the false positive, one term is false positive. We call it as a type 1 error. So we predicted positive. So we predicted positive, but actually it was false, right? So the prediction came out to be positive, but actually it was false. So false positive. So so when you learn this term, because at some point of time it would be little confusing. So when you say false positive, to think in terms of prediction. So it was prediction was false, positive, sorry, prediction was positive, but actually it was false, right? So this part is for prediction and this part is for suppose actual. So this is how you can remember sometimes, right? So in this particular image, you can see false positive, this particular part. So we predicted that a man is pregnant, but actually it is not, right? So this is a case of, so prediction is, the prediction is what? When you say that prediction is false, right? Your prediction is positive. So prediction can be positive and one time prediction can be negative. So that's how the two errors would be distinguished. So in the first case, when you say false positive, so we're talking about when the prediction is positive, but it came out to be false. Second time, when the prediction is negative, but again it came out to be false because it was actually positive, right? So when the prediction is negative, so again it is a false. If it is the case, then we would talk about the type 2 error, right? So like in this particular region, we predicted that the woman is not pregnant, but actually she was. So, I mean, this is a very typical example where which is used while understanding the confusion matrix, because as you go along, a lot of confusion actually gets creep in, right? So, so you might be given a table like this, for example, in the most simplistic case where we have the values. So this you should be able to understand that what is the true, negative, true positive. I hope you by now you're able to understand it. So these are the two extreme cases. And these are the two errors that we have. So obviously we are looking for a case. What is the ideal case that we would always look for? So we would look for good numbers in these two quadrants, but very less values in this part, isn't it? That is what we would look for. Ideally, if it is could be both these values could be zero, it would be the most perfect case. So the two positives are true positives, two negatives are true negatives. And in the most ideal cases, I would want 50-50% of true positive, 50-50% of true negative. But this never happens, right? So, so just an example of 165 distribution, right? So it says, so it's a good result actually. If you see along this, so you have 100 cases which were true positive and 50 cases which were true negative, which is a good case. So out of 165, 50 cases which comes out to a very good percentage. So this is a much very good ideal cases, right? Similarly, the different understandability that you need. So I've already explained what exactly these means, right? So so these terms should be very well known to you. So when I say true positive, so this is a very important term actually. Yeah. So true positive, we normally call it as a sensitivity. My voice is coming? Anyone confirm?
Yes, sir.
Yes.
Yeah, yeah. Just wait. Ah. So So when you say sensitivity, either you remember it by true positive or sensitivity, same thing. So model predicted yes, and the patients have a disease. And actually patients had a disease. True positive, everyone knows it, right? So when I say, so it is very easy to remember actually, right? True negative. So model predicted no, and the actual patient was also not having the disease. I mean, actual also no. So false positive, type 1 error, the model predicted yes. I've already explained this, right? So, so I mean, these are the terms that are required. Accuracy is pretty simple. These are the metrics that we require in a confusion matrix. So accuracy is very simple, right? So obviously the two cases were true positive and true negative. So I added up both these things and divided by total, divided by all the four values, right? So that would give you the accuracy. So what are the actual true cases? Both positive and negative divided by the total cases. So 0.91, 91% is quite a good accuracy rate considered, right? I hope this is clear. So when it comes to misclassification rate, it is the reverse way. You can do it minus one also. 100 minus of 0.91 or whatever you first you calculate this accuracy, then minus one can be used to get the misclassification rate. Or otherwise, you can do what? FP plus of NP, that is the false positive, false negative by total. That is also another way of doing it, right? Then it comes what we say is called true positive rate. Now, true positive rate is a very important thing. Sensitivity or recall, actually, both the terms are equally used over here. So it says what true positive. So so rather than remembering this formula, you should also remember this. What exactly says that true positive means when it was actually yes, right? How often it predicted yes. So it is the prediction part which is important. So what was the actual, right? So when out of all the cases which were yes, actually, out of those yes cases, how many of them were predicted yes, right? So this is called recall, recall, sensitivity. Okay. So remember this because there are another term that confuses it. So, so when we list down what are the true cases or what are the actual cases, and out of those actual cases, how many of them were yes. So true positive. Obviously, we're talking about true positives only. Yes, by the actual yes, right? So true positive. Suppose, for example, true positive is this particular case, and by actual yes. So actual yes would be obviously this particular case, this particular row, isn't it? Actual yes. So it would be Fn plus of Tp. Otherwise, if you remember it with the formula Tp plus of Fn, you could have this called what? Tp plus of Fn. But this confuses you. So better you remember it with actual yes, right? So this is how you get it. Similarly, there is true negative rate. We call it specificity. So when it was actually no, just the reverse part of it. How many of them actually predicted no? So this is true negative rate and true positive rate is very, very important, right? So equivalent to, otherwise you can calculate this true positive rate and then one minus can be done, right? So again, true negative and then actual no. So if you have this kind of table, you can always calculate these values, right? I hope no issues. Pretty simple. Then then comes two different other forms, which we call it as what? The false positive rate and the false negative rate. So we had true positive rate and true negative rates. Similarly, we have false positive rate and false negative rate. So type 1, type 2 error, right? So when it was actually no, right? How often does it predicted yes? So when you talk about false positive, so you associate this false with this no. You would be able to remember. So when it was actually, so the first term is always for the actual term, right? Actual term. So when it was actually false, out of those false cases, how many cases were actually predicted yes or true, whatever? You got this? So the false positive, you have the false positive over here divided by actually all the cases which were no. You got this? So this is how you would be able to calculate it. And similarly, false negative rate. So we predicted no, but actually they had the disease, right? So also known as type 2 error, isn't it? So this is how you can, again with the same thought process, you can put this, right? So there is something called precision and prevalence. Prevalence is not that important, but precision is very important, and you often tends to confuse it with the term called sensitivity, right? So these two terms often confuses you the most. The two positive rate, that is sensitivity and recall, and the other term is precision. So what precision says and how it is different from the recall or sensitivity. When the predicted yes, how often it was corrected. Previously, it was saying that when it was actually yes, we talked about with actual. So out of the all actual cases, how many of them were predicted yes? Now this is a flip. Now from all the predicted cases, yes cases, only yes cases, how many of them were correct actually? So this is just a minor variation, right? So TP by predicted yes. Here we say, okay, got this? So I mean, this might help you a little bit, the explanation that I gave you. And the prevalence, how often does the yes condition actually occurs in a sample? That is simple, right? So this is how you might be given the values. You need to remember either the formula or in whatever manner you find your way to remember the things. That is up to you. So you can always do that, right? So these are all calculations once you are given a values. I hope you should be. F1 is another harmonic mean or the precision and recall. So I mean it is normally used. We have a combination of both precision and recall over here, right? So this is how it works. So if F1 score is high, then both precision and recall of the classifier indicates good results, right? So these are two aspects which can be covered in this single metric. So when this is how it is done, so if you know how to calculate recall precision, you can put this into this formula. I can calculate it, right? So I think this I have done. So I mean, there could be the cases where you may not be given these values as a calculated ones. I mean, I may not give you a table like this. These are the direct substitutions actually, right? So you might get a database like this. So suppose you have y, that is the actual one, and you have the predicted values like this. And then I ask you to, and then I suppose there's an outcome also. Suppose based on threshold, this is the classification. So these three columns might be there for you, for example. And then you have to calculate the rest of the things, right? So if you remember recall says what? If you remember recall में क्या बोला था मैंने? Recall is this. So out of the total actual cases, yes cases, how many of them predicted yes? Yeah. So out of the total actual cases. So what are the total actual cases here? One, two, three. Actual cases, sorry, actual cases. Why? Sorry, actual cases are what? One, two, three, four. Sorry. So these are the true ones. Actual cases are four ones. And out of these four cases, how many actually got predicted correctly? Okay. So you get one case, you get two cases. You get my point? So only two cases. So these were the cases if you're getting confused. So these are the actual cases. You get my point? Four cases out of four cases, you find that this is correct. This was actually predicted yes, and this was predicted yes. Rest nothing. So actually, it was what? Prediction is 2 out of 4, which is nothing but 1 upon 2. You get this, everyone? Now, precision. Precision is says that out of the total predicted yes, how many actually got true? So if you say out of the total prediction cases, how many actual predictions are there? Suppose this one, there are three cases. There are three cases, right? Which were actually predicting one. Yes,
But the
is it?
actual cases are four. Like why
Ah,
we
that's
can see the four as four are there.
These are actual cases. Na? Previous case you're talking about, na? Or this one, or
This
now?
one only. In the precision, we have like true positive divided
No,
by
no,
actual years.
no, no. Understand my point. Um, just let me. What was this precision? When predicted years, how many of them were correct actually? So I would first look into predicted years. You got my point, right? You're talking about precision, na? Now.
Yes,
So we
precision,
would look,
correct.
you would first look, that's the minor difference. So here you would first look into the predicted yes cases. Out of
Okay.
those yes cases, how many of them were actually correct? You got this? There's a
Okay,
minor
okay.
difference. So, so these were the predicted cases. So out of these predicted cases, there were three actually, so three cases which were true, the cross marks. So three, out of this three, out of this three, how many of them just see were actually true? So this is one, no, and this is one. You getting this? So two, but three. Did you get this, everyone? So there's a minor difference. Um, I mean, you would not be able to understand otherwise. I've just gone into so much of details and made you aware. So try to stick to what I've explained, right? Otherwise, formula wise, you would always get confused, right? So this is how you can calculate it. Accuracy is pretty simple. Everyone knows it, right? So, I mean, there could be the case one, case two type of errors, right? I've just given an example. You can always read it. So, I mean, this is very common kind of examples that you would get in front of you. Another important term, which was not the part of the actual slide, I would like to explain this is also very important. You might get questions from this also. I mean, it could be useful in the machine learning syllabus as well. See, ROC curve and the AUC curve, right? So, so what is happening is, what does it help you to understand that how good is the model at separating the classes, especially when the model predicts the probabilities, right? So this is the overall thought process for ROC curve and AUC, right? So they help us to understand that how the model is good at separating the classes, right? And so suppose we build a model like this, for example, these are probabilities it is predicting, right? So, so we need to decide that at what probability should we say that a disease exists. That's a question. It's a big question, right? So if my classes are yes or no, disease yes or no. So what is the probability I would put beyond which at one side yes disease and below which no disease? So that's a big question. And these thresholds can change. Someone can keep a threshold of zero point 0.6, another person might keep a threshold of zero point 0.8, other might be keeping a zero point 0.5. So there's a big question. So this ROC actually helps you study all the kinds of thresholds. So in a way, I have to do something with different thresholds, understand what is the perfect value of the threshold. You getting my point? So the model behavior depends on the threshold, and ROC actually studies this behavior. You got this? Yeah. So ROC actually means what? Receiver operating characteristic curve that we would understand. And it is a graph which actually shows how the model performance changes at different thresholds. I hope you are getting what exactly these thresholds, so probability that we return, right? Now, ROC curve is actually a plot between two values. One is true positive rate and the false positive rate. You remember that we did? So true positive rate, that is recall, and the false positive rate, right? So true positive rate means what? How many actually positives were correctly detected? How many actual positives? So same case, out of the total positive cases, how many were actually predicted? Yes. And false positive, how many negatives were wrongly classified? So out of the negatives, how many were not classified correctly? Wrongly classified as positive. Sorry, wrongly classified as positive only. So out of the negatives, how many of them were actually classified as positive? You got this? So these are the, either you learn in terms of these terms, which is difficult to remember. It is absolutely your choice. So this is the true positive and the false positive rate are being plotted, right? this is, I'll explain this, right? So by changing the thresholds, we can keep changing the thresholds, and basically by changing thresholds, you would always get a curve. So we check with different threshold values, and we can plot a curve, which is an ROC curve. So it's actually a trade-off between what? High TPR and the low TPR, right? So so this diagonal line says where we have TPR is equal to FPR, right? So this entire diagonal line says TPR and FPR are same. So typically, this is the best value I could have obtained, right? So anything in this curve, so interpreting this curve, so the closer to the top left corner, जितना भी ऊपर आओगे आप, ठीक है ना, the better model performance. Diagonal line is a way kind of random guessing, right? You do not have discrimination ability, so you cannot discriminate among the classes. So at any threshold, the true positive rate equals to the false positive rate I told you on these thresholds, on this diagonal line, right? So as a result, the ROC curve lies on the diagonal line indicating random performance. So perfect model would be this. This would be the random guess. So I've given an example actually. For example, you have a binary classification problem, 50 spams and 50 non-spam mails, right? If the random model assigns labels to these emails, the outcome becomes random. Let's calculate TPR and FPR. So if suppose you have zero point 0.5 random thresholds, so you have to calculate these values, right? And suppose you have calculated these values, right? So you can see the zero point 0.5, zero point 0.5. So it lies on the diagonal. Similarly, you can change the threshold now. So different thresholds. So you would have these different values, right? So at every threshold, TPR, when you talk about the diagonal line, it would be always equal to TPR is equal to FPR, right? It's a random guessing case. On the contrary, what AOC does over here, AOC means that area under this curve. So when you plot ROC, so what is the area covered by this would be the ROC, so would be the AOC curve, right? So the overall classification ability. So in a simple sense, what is the overall classification ability? Because in the previous case, I was trying with different thresholds and plotting it. So now I need an overall classification ability, right? So AOC would say that how well the model separates the positive and negative classes, right? So if we have, so these are some of the meanings that you can have. So if you're on a higher side, obviously it is something that we would require. So why RUC AOC is important? Because accuracy can be misleading. Because in the previous cases where we were doing accuracies and some other parameters, right? So especially for imbalanced classes or medical diagnosis or fraud detection, so it actually evaluates the ranking quality of the classifier. So once you decide a classifier, then well, there can be different thresholds at which the classifier is built. You check all those thresholds, and then you decide that which is the most correct threshold value at which we can use it, right? So this is just a little bit more description on about it, that what are the different curves can be drawn, right? So I mean, I've given you a very simple way of showing that how this is built, how this AOC is built, right? I mean, this may not come in exams, but if it comes, then you should understand how actually it does, right? In machine learning session, this can be an important thing for you. You hearing my voice, everyone? Hmm?
Yes.
Yes, sir, you are able.
Yes, sir.
Yeah. So I'll give you a very simple case because normally people would not explain you this. So you have this particular table, for example, right? You would be calculating the probabilities. So I'm not covering that how the probabilities came, right? And these are the classes, right? So what I've done is I've just put this particular table in the decreasing order of those probabilities first, right? We sort the instances in decreasing order of their scores or probabilities, whatever. And then you apply a threshold at each unique value of the score. And then based on which you would be counting numbers of all these four parameters, right? You got this?
Yes, sir.
Okay. So this is what we mean. You just this is the same algorithm that I'm using. So let us do one thing. I'll take an example. So suppose this is 0.95. I take this particular score, for example, right? This is a predicted class. So it says that an instance is classified as positive if its score is, if I'm taking this as a threshold, for example, right? I told you that I have to try different thresholds. I'll try this threshold, for example. So I say that this instance is classified as positive. All the scores is greater than 0.95. So wherever the value is greater than equal to 0.95, the 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 instance that would be there would be classified as positive, right? Rest would be negative, right? So at this particular example on this particular table, only one instance would be there, obviously. This is the only instance which can be thrown as positive. Rest would be negative. Very well understood. Now, based on this, I have to calculate all these values. See, idea was I have to draw that particular graph, right? TPR plus FPR that I told you, right? So the true positive I calculated was what? One. Why? The number of positive instances which are correctly predicted as positive. There's only one instances because at this particular range, at this particular greater than score, there's only one row, right? So obviously, which is true positive, so TP would be 1. What is false positive? The number of negative instances incorrectly predicted as positive. So obviously, there are no negative instance is classified as positive over here. You get me? Because my threshold right now is 0.95, so do not get confused. So in this case, there is 0. Now comes Fn, which can be a little confusing, and you must remember the
No,
number
sir,
of positive.
what about the second one? The second prediction, the plus is
See,
there. Why it is not false
see,
positive?
understand my point. You have drawn this line right now. That is, instance is classified as positive if it is greater than equal to 0.95. Just forget about this table, otherwise we might little confused. So everything would be classified as positive if the score is greater than equal to 0.95, right? Got my point? So first value is clear. False positive
So,
says what? Number of negative instances incorrectly treated as positive. See, nothing can be taken from this, no? So whether you take any of the instances, all the cases would be here is cannot be taken as positive. So out of all the cases, if even if you, because this does not touch upon this 0.95 criteria, no? None of this touch upon zero point 0.5
So,
criteria,
what is the
0.95
meaning of
criteria.
plus minus sign in the two class?
This is a table that we got. Now I'm trying with different thresholds. These are the classes, my dear. Plus means 1. You replace a plus with 1 and minus with 0,
So
right?
what is the significance of this corresponding to
This is
the
a,
score?
this is a
this
true,
is not
this
clear,
is
sir.
always,
This is not
just
clear at
wait,
all. I am telling you.
just
What is
understand my,
uh, no no
understand
sir,
my
it
point.
is what does basically the table signify is this is
See,
instances of word and then scores is
understood.
you're saying yeah. So maybe a little bit of
Wait, wait.
background if you can bring that would be great.
See, simple thing, my dear. So when you have uh, data, what would you do? One is your actual value class is there, na? You have some class. So this is the class, actual outputs. These are actual outputs, which is already given to you. And these are the predicted values or scores. We haven't converted them into prediction, yes, why or no. We haven't done that. We have just calculated the probabilities right now. And these are the actual values which were already given, classes which were already given. You got this? This data would always exist in this form only. Agreed or
So
not?
you're saying okay. Okay.
You got this or not? See, I haven't. See, obviously, there are two things now. One is your actual value. Another thing that we want to calculate is what? the predicted value. So I haven't calculated predicted value. Predicted value would be calculated, right? So right now, instead of predicted values, I have calculated the threshold, the probabilities for each of my instances, whatever may be the instances may be. I have not taken any example, right? You got this? So what I have calculated here till now is the probabilities. Now, out of these probabilities, I have to set one threshold value based on which I would decide that above that threshold there would be all pluses, and below that threshold everything would be negative. I mean, I have to decide the class, and this is actual classes which is given to me. Still, you not got? Did everyone
Okay.
understood or not?
Yeah, yeah, yeah.
It's a
Yes, got
simple
it.
table. It's a very simple table. Now, what I'm trying to play around is with that what should be a good threshold. I'm just giving one instance. Many such things have to, many times, many different thresholds would be tested. So how those thresholds are tested, that I'm trying to tell you. So I'm taking one threshold. That threshold I took it, suppose 0.95, and I'm saying, what I'm saying, like I would consider all the values to be positive with this condition. Rest everything would be treated as negative.
Negative.
You got this? You got this
So
or not?
so from
Huh.
instance 2 onwards, everything is predicted as negative.
You got this now, everyone? Yes or no?
Yes, got it.
Everyone got?
Understood.
Huh.
Yeah.
Now comes this Fn, false negative. So number of positive instances incorrectly predicted as negative. So what are the number of positive instances? First see.
Oh,
पहले अपने डेटाबेस कितने पॉजिटिव इंस्टेंसेस थे वो देखो आप लोग. हाउ मेनी ऑफ देम, से फॉर एग्जांपल, ऑब्वियसली ये वाले केसेस में आप देखोगे तो नंबर ऑफ पॉजिटिव इंस्टेंसेस विच वे इनकरेक्टली प्रिडिक्टेड एज नेगेटिव, अब देखो कितने हैं, check.
4, 8,
1
2,
is 2,
6.
6, 8, 10, isn't it not? So 1 is 2. So और number of positive instances मतलब actual instances 1 के ज्यादा है कितने देखो, 6 है, 8 है, 10 है, यही थे पॉजिटिव इंस्टेंसेस, है ना. बट दे आर ऑल इनकरेक्ट बिकॉज मेरा तो रेंज आता ही नहीं है ना, मेरा तो रेंज अभी क्या है 0.95 है, तो सारे के सारे नेगेटिव केसेस में तो हुए ना अभी तो. यू गेट माय पॉइंट. ऑल वुड बी ट्रीटेड एज नेगेटिव बिकॉज माय रेंज इज नाउ right now is 0.95. Agreed or not? Did you get this, everyone?
Yeah, yeah, yeah. Now it is
Yes,
clear.
yes.
Yeah. Hmm. Similarly, you can calculate Tn also. That is number of negative instances which were correctly predicted as negative, right? So number of negative instances were what? This 1, 2, 3, 4, 5, right? 5, obviously, and they're negative. Why? Because it is not in the range of 0.95. You got this or not now? I hope you should because I've explained in a very simple way. It's not a rocket science at all. Everyone got this? Hmm?
Yes, understood.
So similarly now you would try on different thresholds. Now I have tried suppose 0.25, right? Then I would try something else. Actually, you try each and every threshold. Actually, when you do programmatically, you have to try each and every threshold and calculate all these values now. I hope now you would be able to do with this 0.25 also, right? So any value which is above than 0.25 would be positive, rest would be negative. So you would be able to calculate these, right? Now this is how you would actually get then, right? So this is what ROC curve is. So you get what? So at different thresholds, these are different thresholds you tried, you calculated these, and then actually once you calculate these four terms, you would be able to calculate TPR and FPR. And then you draw these, then you plot these two TPR and FPR. You got this now? First, hmm? Everyone? Now, actually, I mean, out of once you do so, how you again this would no one would be telling you that how do you calculate the AUC, right? Graph till over here is okay, but again there's a mathematical interpretation, although it is not covered anywhere. I've just given you for the understanding. So suppose I have these kind of values, FPR and TPR, for example, right? So how do you calculate the AUC? Because ultimately you would be calculating a single value. Ultimately, you need one value, no? You get my point? So you can pick up from this graph also. That is one way people do it, but there's a different way of doing so. We call it as a trapezoidal rule, right? So how do we do it? Just forget about these formulas and all those, and you can just take it as it is. So this is so you would be applying this kind of trapezoidal rule would be applied to approximate the area under the curve by dividing it into different trapezoids, right? So just forget about what exactly it says. Just understand how it is used, right? So we're calculating the AUC, and there would be a base 1, base 2, TPR1, TPR2, and this is how the height would be calculated. I'll explain how this is done, right? So understanding these examples, suppose I've taken these two instances first two instances, right? The first two instances I've taken. So I have to take the pairs of the instances one by one. So I've taken point FPR starting from point 0.0 to 0.2 and TPR starting from point 0.0 to 0.4. I mean 0.0 to 0.2 and similarly 0.0 to 0.4. So this is I'm talking about. Then you calculate the area. So then you fit in every value which is there. That is, this is TPR1 plus of TPR2. TPR1, TPR2 is the first two values, point 0, zero point 0 and point 0.4, this one I've summed up, and then the difference between FPR, these two differences. Okay, so there's a simple thing. So you don't have to do this mathematics, but I'm just getting you the background part that how actually it is done. So you calculate different segments similarly, then you move on to the second value, that is from this to this, point 0.4 to 0.6, point 0.6, 0.2 to 0.4. Then you again calculate the segment 2. This is how you calculate different segments, and then you sum the total AUC, the sum of all the segments. We get this kind of thing, right? The area under curve is between this 0.58. It provides a summary of the classifies ability to distinguish between the positive classes, right? By graph also, sometimes people pick up some random values directly. They may not do these kind of calculations, right? So model performs better than random guessing. So this is how you actually get a suitable, I would say, threshold based on which the things are done. Got this? So there's no rocket science involved into it, but you must know it. Okay. And if you really wanted to achieve a better usage, then you have to go back into your data and do a lot of other things, that is fee changing, model tuning, class imbalancing, better threshold section selections. So all these activities can be done. Okay. Right. So we'll move on to something called multi-class classification thought process also. Okay. Which is important. Just wait. Yeah. So So, I mean, everyone understands till now we had only two classes, to be very frank, right? Zero, one, or whatever you call it, plus, minus, whatever. That is the binary classification. For now, you have to talk about what? Multi-class. That is, we can have 1 to k classes, right? Whatever you can think. You can have different categories of classes, and therefore the things would become difficult without any doubts, right? So you need data, obviously, with multiple labels. You have linear model with k output neurons. So obviously we have to model everything in terms of these neurons only, right? So that is also one of the things that I have to do, isn't it? So that is also that I have to take care that whatever I'm talking about, it has to be in terms of the neurons, right? I hope uh, everyone knows that whatever we are doing, whatever classification or machine learning thought process that we are doing is all in terms of neurons. Yes or no? So do not start, I mean, getting back to the simple machine learning thought process. So everything that we do here is in terms of neural network approach. So we would be using softmax function. You remember anyone? Why softmax function? Anyone remember? We did activation functions इसलिए मैंने पहले ही कराया था एक्टिवेशन फंक्शंस. You remember activation functions? Anyone? Hmm? Or forgotten?
Yes, I remember.
Yeah. So that's the reason I wanted, because they have also in slides they cover activation functions later on, which is not the correct thought process. So softmax function, if you remember, it used to give you the probability distribution. You have to just go back and revise it if I have, if anyone has. And we would be using the categorical cross entropy loss. Now, why we would be using this, I'll give you an example also. And then you have learning algorithms. Mini batch stochastic gradient descent would come out to be a better. Simple stochastic gradient can be used, but it can be little, I would say, in non-efficient, right? So efficiency would actually come from batch or a mini batch stochastic gradient descent. And if you remember, we have done all the three kinds of such gradient descents, right? These are just generic. There's a part of the PPTs how the input features would be presented. I hope. Can anyone tell me what um each of these, I would say, columns would represent? Can anyone get a guess? For example, this
Features.
is
Vectors,
column.
vectors,
Anyone else? No, vector. It is always, it is definitely a vector. I mean, what this each,
Features.
features,
Features.
any more addition, which obviously these are features, but anything which is related to multi-classification. Here we have multiple classes. So any thought process? So actually, okay, I'll take it further and then I'll explain.
independent data, not linearly dependent.
I'll come to that part. No, nothing is there. I'll explain you. Just give me some more time. I doesn't want to. So so obviously we need first representation of the classes, how the classes would get represented somewhere, right? This is obviously the input feature in entire data, right? But how the classes would get represented, that also we have to understand. So either you go for integer encoding or one hot encoding. Everyone knows it. I don't have to, but obviously integer encoding can be useful when we have very less number of classes, one or two or three, I mean three or four, that is okay. But obviously I hope you have done machine learning. Integer or label encoding is never considered to be a good one. Anyone can give me the answer? Why label encoding may not be a good thought process if you have, if you're doing machine learning? Any thought process? No? Why label encoding? See, we you must have learned label encoding and one hot encoding. Why label encoding may not be a good thought process?
Too much of processing on string.
Not processing, not at all, not in terms of processing at all. Any other thought process? No, because when we go for in label encoding, so suppose I have labeled something like I have 10 classes,
Uh,
maybe some
because it's a we are converting categorical text data to numerical
numbers.
data. So
Yeah, yeah. Then,
um
so you
sometimes uh
yes, yes, you are almost correct. Yeah, please complete it. Sometimes what happens?
because sometimes what happen if we have like give an example like if you have alphabet like A B C D, so
Hmm.
sometimes it's when we are like converting into numerical like it's taking the sometimes it's taking the alphabet wise also like if it is giving let's give example my name Tanushree, so sometimes it will be maybe because of the number of words we have, maybe it's greater than the other numbers, something like that it is.
So she's almost correct, but probably statistically she was not able to explain. So if this is the case of these four classes and I've labeled them like this way, label encoding, right? For me, for the data, all the classes are important. But statistically, it may happen that my data may start favoring a higher value or a vice versa. Statistically, it can always happen, right? Because everything got now converted into statistics. All the four labels were important. But now, while calculations, because 4 is greater than 1, definitely it might get a favor statistically somehow. So this is never a good idea to have label encoding. So statistical interpretation gets deferred, although all the classes were of equally importance. But statistically, this bigger values might get favored, or somehow some other, I mean, one may be favored, may not be, I mean, in comparison to 2 or 3 is a lesser value. So somehow it might get. So that's the reason we use methods like one hot encoding, or we convert them into some kind of similar to one hot encoding, right? And I hope everyone remembers one hot encoding is that I would have, say, suppose a sequence of 4 bits at one time, right? So this could be one hot encoding. At only one point of time, one of the bits would be higher. So it has a suitable variance and a good representation of the variance when we talk about the classes. Anyway, so this is how we can represent the classes now. It would be a better representation. So it treats all the classes equally. That is the important thing, right? So there does not get anything called implicit ordering, right? It matches the format of softmax probabilities, which is very important for me, right? And then simplifies the loss computation. Standard is a very standard process here in deep learning. Okay. Anyway, so once we have these yeah, yeah, please.
Yes, sir. Sorry, Nuda, but isn't that what you just explained is a part of scaling the
Yeah,
input
we
so that
see we do not we never scale the output classes. We scale the features. Understand my point? Yes or no? We
yes, sir,
scale
correct.
the data portion. We do not scale the classes. So that's the reason. Otherwise, if we would have scaled it, it would have become equally very difficult otherwise.
Understood.
Yeah. So when it comes to, so I told you for multi classes, now I have to start thinking in terms of neuron approach, right? So multiple classes, one neuron is not enough. Why this is said? Anyone? For multiple classes, one, अभी तक हमने जो भी किया, we had one neuron for binary classes, है ना? We may have good number of features, that is okay. For features, I may have any number of neurons in the first layer, but one neuron, I mean, sorry, till now we had only one neuron in the binary classes, and we had only one neuron, and whatever may be the number of features. I mean, till now we had the approach like this. So whatever may be the number of features, I could have drawn like this, and there was only a single output class, right? Now, this approach will not work. Anyone who would have any justification?
So the output
Because I have.
neuron is, sorry.
Mhm. Yeah, please.
Yeah, so my understanding is output neuron has either 0 or 1, considering the probability distributions and thresholds. In this case, since we have multiple classes, let's say for K, for example, we can have one neuron for each of the class, which can give a 0 or 1 depending on whether the class is the one
So,
that
in a,
is
yeah,
considered.
absolutely. So, in a way, what he's saying, I'll simplify it, because every class needs a different distribution, no? They needs their own distribution, own representation of the weight matrix and the input. है ना? So, in a way, very simple sense, then each class would have a, because input would be same, input would be same. You agree or not? The weight distributions would get differed depending on what is coming to what particular input neurons, right? So every class must independently decide how much do these features support me, isn't it? So obviously, if there are suppose 3 classes, so all these 3 classes would have their own representation with respect to the input by having the different combination of weight multiplied by inputs. So every class must have its own pattern. That's the idea. Each class gets its own neuron and its own weights. Then only it would be able to. Otherwise, how would I understand that this neuron is important or that neuron is important in classes classification? I need one of the neurons to kind of win, isn't it? So over here, this might be representing, this entire column might be representing class 1, this might be representing class 2. This is how it would work now, right? You got this? So each column would represent the weights of for class, different classes, right? So this is how I can look into it. So Z1 gets a different representation for the inputs and the different weights, because it has some different weights as compared to what Z2 receives and as compared to ZK receives. Everyone gets a, but inputs are same, but they get a different representation of input multiplied by weights. Agreed or not? So here the softmax, so everyone would be coming up with their own different set of probabilities. So whosoever wins in that probability, that class would win. And that is how we would say that that class has. So this is one class, this another class is another class. So every, this we call it a logits. You know? So every class would have its own representation of neurons. So, and softmax would convert these scores into probabilities, and each class would get the probabilities. And I hope you remember it. So this could be kind of thought process that might be written, and after calculations and after softmax functions. So I would definitely say that yes, this class 2 is getting the highest probability. So I would turn this into, and the beautiful part is that if we add up all these, it would be not greater than 1. So everyone knows about this approach, nothing new. So I think this can be skipped, the same thing. So the softmax function, everyone knows. I have not to repeat this. I've done softmax function before also. Softmax, I've just given an example also. If someone wants to understand it, I've done before also. So not an issue. You can do this. Categorical cross entropy loss. This is important, right? That the loss function that I'm using. So we need to little bit understand upon this also. So this may look very typical, but it's not actually very typical, right? So these are the you have number of training example. I mean, it mathematically it might look little confusing. So number of classes that we have k, right? And we have the actual class labels, and we have the predicted probabilities, we have the total loss, and the weight function. So actually, if I just sum it up, that what exactly this function is talking about, we can do it in simple manner. You compare the actual answers with the predicted probabilities. For all the things, I would do that for all the classes and all the training samples. So you have classes as well as the training samples. Then you compare the total error. So I'll do it for you. Based on this, I'll give you a working example. So this could be a simple, you can see that loss depends only on the predicted probability of the true class, isn't it? See, you can see that what kind of loss is being calculated. So what is the relationship that you see that where so I mean the prediction which are good, they have a lesser loss or a small loss, obviously, right? So heavy penalizes confidently wrong predictions. So wherever there are wrong predictions, very bad. So the punishment is heavy. So this is the entire thought process of categorical cross entropy, based on which it entirely works. So loss increases exponentially as the predicted probability for true class decreases. You can take this particular example. It always gives you more confidence. So suppose I have three classes, for example, this, right? So what I'll do is I can represent the input features like this, for example, and these are some of the values that I have taken just for understanding point. And this is suppose randomly taken weights, for example. So I told you each of these columns of the weights now would representing to each of my three classes, right? So then I could do what I can compute these simple logics, right? Everyone knows what this is. So I have done for Apple, and rest of the third class also would have been computed like this way. Everyone knows how to calculate it. Finally, you get this, right? For example. So these are the raw scores, but not the probabilities, yes, right? Then you definitely apply your the softmax function. So you might apply it on these three values. So after doing this, you can sum up all the exponentials that you got it, right? And then what you do is you compute the probabilities, right? By applying the softmax. So that is how you get. So obviously you see that banana comes out to be a winner. So the class would be this, but the final predicted probabilities should not be more than one. Obviously, that is what we were trying to say. So the final prediction, suppose this is the one banana, and then the actual class prediction is mango over here, right? But the actual class prediction was suppose mango, right? So then the one heart encoding we would represent the mango was one heart encoded like this. So I'm trying to come to a phase where I would calculate that loss using the categorical law cross entropy. That was the idea. So it gave me banana. Actually, it was mango. So banana is represented by this, and the mango is represented by this numbers, for example. Then you compute the categorical loss entropy. Yeah. So I mean, you compute all this. I think it's not rocket science. You can go sit back. Ultimately, you calculate this loss. So loss is large, right? Because the actual class was mango, but the model gave only 0.85% or whatever, right? Whatever, 8.5% probability to mango. So bad prediction. Thus, the cross entropy strongly penalizes it. That is what we wanted to do, isn't it? Because the final loss is quite big. So, I mean, haven't completed this. You could have completed this just to showcase that what exactly this the categorical loss entropy does. Obviously, the rest of the iterations would happen. So, did the model give high probability to the correct classes? If yes, small loss, and if no, huge losses. That everyone knows, right? So, I mean, these are some of the advantages. You can always read out these advantages, right? The heavy penalization is something that works quite well. It works quite well in the favor of softmax, and then by nature it becomes convex also. So everything is helping out. Then you can move from the SGD to mini batch. I've already explained you the thought process of mini batch and the batch SGDs. So that should not be a difficult part from any angle, right? So how it is useful, I've already explained these things, right? So you can always sit back and understand. So suppose if you talk about batch gradient, or everyone knows what happens. We use n examples per update, slow but stable. I've explained it in my own way in previous slides. What about the stochastic gradient descent? I've explained that. What is mini batch? I've explained that, right? Advantages of mini batches I have explained before also. Some of the key concepts. I think I've already covered this, so I would not cover it again. Rather, we would now shift to something called, I'll put this slide, right? We would start covering the next session, which is, so we have some time, so we can start this next session as well, which is very important. And yeah, now we would be moving towards more difficulty level, and we would be moving towards something called, I'll open the back propagation network also, which I have my own slide, which I would be able to explain it much better. Anyway, so the next we would move on to something called deep feed forward neural networks, and the actual what we call it multi-layer feed forward networks. We will start from here. Till now we're solving simple problems. Now typically with this higher set of networks, we would have higher hidden layers. We would have full functionality of hidden layers, right? Till now we were able to solve very simple problems, whether it in terms of linear regression or whether in terms of simple classifications, right? So everyone, I'll give you a simple thought process. Everyone knows about it, how it is modeled and everything, right? Many real world relationships are non-linear. So ultimately, the idea, what they're trying to say is that everything cannot be linear in nature. We talked about before also. So non-linearity becomes very important, and therefore, non-linearity we must have the higher high introduction of the layers now. Single neuron would not do. You need to have multiple layers, and we talked about this thought process much before in second session itself, right? So whether these problems called image recognition, natural languages, they cannot be just solved by a single neuron model. You need much complex representations, right, for different features, right? So, I mean, they started with this XOR problem. We solved this XOR problem in much earlier in our sessions, how the XOR was solved using multiple layers. I hope you remember that. So I'm not repeating this portion. We did it much earlier. So how the XOR problem could be solved by a thought process like this. Yeah, you remember everyone? We solved this XOR problem in our own way using multiple layer. Yes or no? So they're repeating this thought process in this slide. Can you hear me, everyone? Yeah.
Yes, sir.
So I'm skipping this. I'll directly come to something called back propagation network. So you can take my earlier slides where we solved the XOR problem using MLP. We started whenever. So when we first time talked about MLP, I solved the problem of XOR for you, right? They have given their own ways, but I've talked about this much better way and explained you the entire thought process. So so what is nonlinearity? We talked about this before. I gave you this thought process much earlier, right? That this is a function f is nonlinear if it does not satisfy the linear property, right? So why non-linearity matters? We talked about this also because deep networks collapse to a single layer models, non-linear activations enable learning complex patterns. We talked about this much before, right? And we talked about these kind of activation functions that would be helpful in creating or introducing the non-linearity, right? So so this gives you a little bit of understanding between the different activation functions, right? So the kind of ranges they give us. And I also talked about leaky ReLU, if you remember, right? Whether they are differentiable is very important for me, isn't it? So ReLU has a different purpose, so it's not about differentiability for which it is used. I hope you remember, right? So so normally we use sigmoid in the sigmoid and ReLU in the sigmoid at the outer layer or softmax at the outer layer and then the ReLU in the hidden layer things. Vanishing gradient, we talked about it before, right? Now what I'll do is I'm not getting back to these ReLU and all those because they as per these slides they are covering at this stage. I've covered it much before. I'll directly come to something which is called one of the most important networks that we all have to do it much carefully and very important, which is the um, deep feed forward neural network, where we would have multiple hidden layers and multiple inputs, right? So this is how I would be. I mean, this is same thing. It's not that deep does not mean that till now what we were doing is what uh, the introduction of what multiple use of multiple hidden layers. That's the only concept, right? Multiple hidden layers and the complex data. So data would be or metrics would be always represented in this way only. And a target matrix or the classes or the output would be represented. Multiple outputs would be able to see whether in the form of regression or whether in the form of classification, right? And then obviously, either you would be touching upon mini batch or mini batch, how, I mean, mini batch or batch or simple gradient descent, that depends, right? So common batches, I've already gave you, these are the sizes if we talk about batches. So this is how a typical deep feed forward neural network would look like. So you have multiple hidden layers, right? And then typical output layers, which can be many, would be in front of you. Now, what I'll do is because now most important thing is you need to understand there are two things. One is feed forward calculations, another is back propagation, right? So when you do feed forward, obviously these are some of the weights that you would be numbered. So you would be calculating this value first, you would be calculating this, and then once you calculate this, then obviously there would be some weights around this. You would be calculating this value, this value, this value. Then you're moving in a feed forward direction. Ultimately, you would be calculating y1, y2. Y1, Y2 would there must be having some kind of I would say output values already known to us. So these are the calculated values. So but there would be some calculated values at both the output gates. So obviously then we would need to calculate some kind of errors between what was the actual predictions and what is the predicted predictions. So based on this, I would be calculating something called error, right? I'll be explaining this entire process, right? I'm just giving a thought process now. Now this error, using this error, I obviously because there is, we call it loss, right? We have been seeing it around using MSE or the cross entropy losses. Using this error, I have to adjust my weights so that ultimate target is that the y difference between y and y dash. Y and y dash means y is suppose actual and y dash is suppose predicted value. The difference between them can be minimized, right? So once I calculate the error based on any of the formulas, whether we use any, there can be number of other formulas that we use. Normally we would be using um, approach of gradient descent only, right? So once I calculate these errors, I would update all my weights now based on this error. Based on this error, in that process of retreating back or using this error to update the weights in a backward direction. I cannot use this error to update my weights directly at input and hidden one. I cannot update these weights directly. So using this error, I have to first update this weight between hidden two layer and the output. Then I would be calculating the error at this part. I would be calculating the error at the hidden two layers or hidden two neurons. Once the error would, so the entire error got distributed as errors into these hidden layers in a backward direction. Similarly, the errors which got calculated over here, which are dependent on this overall error, again I would use this to update these vectors, these weights, all the weights between hidden 1 and hidden 2. The same fashion, the errors at hidden 1 would get updated, right? The error values would be calculated, and using those error values, I would again go back and update the weights between x1 and hidden 1. You trying to understand what I'm saying is? So it is a thought process where which is a multiple iterations of feed forward and back propagation of errors. This iteration would continue till for a given input and for a given output that I have calculated, I can minimize the difference between them, and I can say that yes, for this given input and these set of the adjusted weights, so this is my learning is right. So this process would be called as feed forward and back propagation, which we would try to understand, right? And it is quite a difficult process in terms of when we do the calculations, and I expect that everyone would be very attentive. So what I'll do in between, I have a very simple example because at times students get confused a bit. I'll explain it with one of my older examples that would give you a very nice thought process, right? And that actually would help you to understand it, right? This is a typical architecture or network that I have created, right? Obviously, this is your input layer. This is your hidden layer. I have taken one only hidden layer, right? And this is your output layer, for example. Okay, all are please be attentive, right? So this could be little calculative and little difficult. Things would now become difficult from now. You all hearing me, right? So these are just for the significance part. I've used these symbols. So do not get confused with these symbols, right? So we would first understand the feed forward. Feed forward means the direction would be from left to right. So ultimately feed forward means I have to calculate the values of alpha and beta as the output layers, and then I would be calculating some errors, right? Got my point? So you see, I would first calculate the errors of output neurons. Where what are the output neurons is? That is alpha and beta. Yes or no? So alpha and beta, right? I've just given you the formula based approach. How this formula came, I would explain later on, right? Just understand that how the entire thing might look like and how it could be little complex and how it could be little mathematical now, right? So the what are the errors? So this first thing, once I do the feed forward, I have to calculate what is the error at alpha, what is the error at beta, and uh, knowingly I have taken two output neurons to make it a little more complex, right? So I have calculated the error at alpha, error at beta. Error at alpha is what? Understand this. Error at alpha is of two terms. One term is this one, and other term is this one. So this is target alpha minus of output alpha. It means what? At this particular neuron, there would have been some target value. We would call it, say, suppose target alpha, and there would have been some calculated value. So I have accordingly named it by the same name. So there would be the outputted value, the predicted value, and the target value. So difference between the two. You got this? No issues? At every output neuron, there would be the difference between the target and the output, which would be calculated, right? And there would be one more term, that is, what is the actual output which was produced at alpha multiplied by 1 minus of output. How this formula came, I'll explain later on. Just respect the formula based approach, what is happening, right? And how this came from the chain rule. I'll explain the chain rule little later because that would create more complexity, right? Similarly, I would be calculating the error at another neuron, that is the output neuron at beta. Did everyone got this? Just forget about this formula, how this formula came. Any issues till far? So
So
what I'm
we
trying
are
to say is what?
so
Yeah.
output alpha value is always between 0 to 1.
So just forget about what is the value, right?
So it is
Right
1 minus
now,
alpha. That's why.
no,
It
no,
says
no,
1
it
minus
would
output
be,
alpha.
no, it would be the probability what we would be calculating, right? There would be some target. I'll explain it because everything would be in terms of numbers now. And I just forget it what you did. So there would be, suppose the target value is suppose 0.5, right? And
Hmm.
I might calculate something called, say, suppose 0.35. So this is
Hmm.
kind of values I would be calculating now, right? I'll show you
Yes.
later on, right?
Okay.
No. So actually this is nothing but the loss function. To be very frank, this is nothing but a loss function, but I'll explain it later on how this came, right? It does not came directly. It's a complex mechanism now, because till now everything was very plain and simple because we does not have too many things in between, right? But now too many things have got inserted, right? Similarly, now this is the first thing that I will do. I've just projected in terms of formula. The second thing what I told you is, now I would, once I have calculated the error here and here, I would use this error in some way to update these weights. Obviously, these weights would be updated using the gradient descent. In a way, what is the error and what is the rate of change of Wi? I would be using this concept. We have explained it before also. So what is the change in the weight, or in fact, what is the change in the error with respect to the change in each of the weights? But now, using this error which I've calculated alpha and beta, I would first calculate the errors at this layer, that is between the hidden and the output layers. So all the weights which are predicted or projected over here, these must get updated. I cannot update these weights now. You got this? That you have to remember very nicely. So the change in the output layer of weights, I mean, now I'm changing the weight, suppose for this one. This is what? WA alpha. You see, WA alpha. This is a new weight. So the older weight plus this is the change. What is the change and how it is, correlated? Recently, I have calculated this value, isn't it? I just calculated this value. Error at alpha. So error at alpha, the learning rate, and what was the output at A? What is the output at A? Output at A, matlab, there would be some kind of output value that I would have obtained in the when I did the feed forward, isn't it? Agreed or not? I would have calculated some value at A. I would have calculated, right? When I did a feed forward, I mean, when I started calculating from left to right direction, I would have calculated the value of A. So when I'm updating this particular weight, understand my point. When I'm calculating A alpha, I'll remove this. Too many things have, just wait. Too many things have start diagram wise. Yeah. So just wait. So when I would be updating these weight, right? While I would update this weight, so it is dependent on what? It is dependent one on the error which I calculated here. One is the output which I got from here, and also the learning rate. That is how you see the older weight plus learning rate, output at alpha, and the error which was calculated. You got this? Similarly, all the weights, here we had 6 weights. You see 1, 2, 3, 4, 5, and 6. All the 6 weights will get updated. This formula is no rocket science at all. You see, everywhere we are doing so, same thing. So obviously, so if I'm taking care of, if this particular line, if I'm taking this particular line, so what I need to remember is what is the error which I calculated, right? What is the output I calculated A, and then the learning rate and the previous weights. That's the only thing. Can you understand it by symmetry, everyone? Yes or no? If I have to calculate this particular line, so what I need is what is the output which was calculated here, what is the error which was calculated here, the learning rate, and the previous weight. Everyone understood this by symmetry? Yes or no? Any issues? Everyone is able to hear? Any issues still so far?
Yeah, got it.
Yeah, got it, everyone?
Yes.
Now what would happen is, what I have done is I have calculated these new weights actually. I have updated these weights. Understand my point. Now, what is the next task? Anyone? What should be the next task?
Update the
What should
previous weight. Omega A.
update the
W
now,
omega.
which I cannot do directly. Understand the point. I cannot do, I cannot touch this weight directly. See, if in order to touch this particular weights, what I did, I calculated something over here. Understand my point, isn't it? I calculated the error over here. Now, in order to update this particular weight now, I have to recalculate this value. I have to get the proportion of error which was calculated over here. I have to see what proportion of error actually contributed now to A, B, and C. You got my point? It happens in a very systematic way. This is called chain rule. I'll explain it later on mathematically. So now, using the updated values of these new weights, I would update the values of A, B, and C. You got my point, everyone? You have to respect this because everything happens in so sequence. So now you see, I would now recalculate and I'll call it error now. What are the back propagation? So I'll calculate the error at A, B, C. I've started using the term error. You got my point first? Now, how does it happens? So I'll again remove this so that these this does not confuse you a bit. I'll use a different color pen just for the sake of it, right? Now I have to calculate this. You got my point? How would I do so? Anyone who can give me a thought process? In order to calculate this value, what should be kept in mind? Anyone? What all factors would matter? In order to calculate this, obviously this would
Output of
matter
A.
right now.
Output of A.
Obviously this is connected with this layer and this layer. So in order to calculate A, this would have some effect. Even this new weight which has been updated before would have some effect. Agreed or not? Yes or no?
Yes.
Yes, right? Because these are connected with these two weights. So please listen very carefully. Now things have changed, right? Things have would become very complex now. Similarly, if I have to calculate B, so I have to see that who all are connected with this. So the effect of this and effect of this. If you see logically, the error at alpha and beta actually got distributed between these weights. You got my point? And now if I have to calculate A, B, C again, then I have to see the different distributions of error. So actually the error is getting distributed backward direction. You getting my point? Now, if I have to calculate A, for example, how this formula would work? The formula would work error at A now. It would be what the terms, these four terms would use. In fact, this terms would be used. One, in a very simple way and use logical interpretation. Output at A, what was the output at A multiplied by 1 minus of output? From where this term would come? I told you that I will explain everything with example and everything, but right now I just wanted to cover the concept. Therefore, I have fitted this in terms of examples. So I have to calculate. So in order to calculate, again, I am telling you one more thing. If I have to update this as A, then I need both the things. I need what was done here and what was done at the connecting lines, right? So what was done at A? It was simple. It was this particular term. Got this? What was the output at A into 1 minus of output at A, right? So this A, so the contribution of A would be output of A into 1 minus of output of A, right? And rest of the contribution will come from what? WA alpha and WA beta. You got my point? You got my point? So the rest of the term is what? EC. Now WA alpha was what? WA alpha is this term. WA alpha, and there was an error associated at alpha. Yes or no? WA alpha is not separate. WA alpha is the new value, plus value, sorry. This is the plus value, what I calculated over here. Right? So updated value of WA alpha, the error at alpha. Error at alpha is what? We calculated error at alpha. Are you able to get this thought process, what is happening? And it is so, you might see the complexity laid behind it. So in order to update this A, some component or some value which I calculated A was important, and then the combination of WA alpha and the error at alpha. Similarly, the WA beta plus or into the error which was calculated at beta. You see the error which was calculated at beta. Did anyone was able to get this thought process? How things are happening? Anyone?
Yeah, got it.
Or you got confused? It's
No, no,
nothing
got it.
rocket science.
They're a bit
It's a very
confused.
simple. Why you are not actually listen to? I mean, it's not at all rocket science. It is very simple thought process, and that's the reason I didn't explain the formulas how it came. Otherwise, it would have made it so very simple. First, you have to calculate the error at alpha and beta. How I got calculated, how I calculated that error, I gave you a formula, right? And I told you that I'll explain the formula. But the formula is a logical thought process. So in order to calculate this, I told you that if I have to calculate the error over here, so what all terms I used? I told you that output at alpha, what is the value that I got at this? So whenever you take, in fact, actually it became what? It became something like this. A to, I mean, this mouse, I have to use some writing pad, I suppose. Next time I'll purchase one writing pad. Otherwise, mouse is not enough. Yeah. So actually, A to alpha. This is the arrow that I have to use, isn't it? A to alpha. So I would, in order to get the error at alpha, I would calculate what is the output that I calculated at alpha first. Output everyone knows. I would have calculated output, isn't it? So how I use this output is very simple. Output at alpha into 1 minus of output alpha. This is how I got from a formula. How that formula will came, I'll tell you. And there's another term. What was the target value at alpha? And recently, what is the output at alpha? So the next term was what? Next term is the target alpha and output. So this is a formula based approach, right? So I first calculate the errors at alpha and beta, error and beta, alpha and beta, sorry. Now these errors, I would call it suppose error 1 and error 2, whatever. Now I would use these errors to update these weights, right? To update these weights. And how I use this? So if I have to update, suppose this particular weight, so what I did is, what was my older weight, right? Plus the error which I got at alpha just now, you see, the error I got at alpha, and what was the output? Because this WA alpha is associated with A also, and it is associated with alpha also. Both the terms would have its own representation. So error at alpha, what was the, because here I did not calculate error till now, so obviously the output portion of A would get placed. See the output portion of A would get placed, and the learning rate. Did anyone get this now? So this is how it is, all symmetry, and all the weights would get updated. Got this? Now, once all the weights would get updated, I have to recalculate the value of A, the value of B, and I'm moving in a backward direction right now. I would move backward direction till what? Till I calculate all these weights. I do not have to calculate this. Why, anyone? I do not need to calculate this. Why? Because these are inputs. How can I
These are
change these
inputs.
inputs? Right? Inputs would always remain input, right? So I have to keep back propagating it till I update the weights between these first input layer and the first hidden layer, right? So I would now calculate ABC. So ABC, I have to calculate the error. Now I have started calling it error. Why? Because error was getting propagated, back propagated. We calculated error, the output gates, they got these errors were used to update the weights in the hidden and the output layer. Now they would also affect the output which is calculated at A, B, C, right, previously. So now we have calculated error at A, because I cannot touch upon W, this particular weight, unless, because this is associated with A and this one. I cannot directly, this cannot have a directly effect on this. Understand my point? So you have to respect that connections also. You got my point? So it is only I have to calculate the error at A, recalculate the error at A, B, and C. So how I calculate the error is again a formula based approach. Very simple. So if I have to calculate this A, so what was the outcome which I received earlier? It would be important. So So this term would be used. Why this term would be used, I told you, I will explain later on. And now, what other terms would be useful is, now this A is not only associated with alpha via, it is also associated with beta via WA alpha and WA beta, isn't it? So both will have its own representation or contribution, right? So one error would be coming from here, one error would be coming from here, right? So, and recently I have updated my weights, so they would also be party of it. So, so new weight, this is plus sign, right? Remember. So new weight, an error which was calculated here. Similarly, new weight over here and the error which was calculated here. You see, it's a very symmetric thought process. The same thing would happen for each and every ABC. Did you get it now? You have to sit back and understand because you might get lost into formulas. You know? You got this? Should we move further? Now, what should happen next? Anyone? What has happened next now? This is what? What is happening now?
New weights.
Now these weights, now I have calculated something like this. So once ABC is calculated, now I can touch upon these weights also. Yes or no? So now in order to touch these weights, the role of input would also get into there. Agreed or not? Yes or no? Because this line is what? So A and this
Yes,
input would also come into play in order to update this. Agreed or not, everyone?
yes,
Yes?
sir.
So now see, so older weight, learning rate is always there. It's input. And now I just calculated the error at A. Simple. So nothing rocket science. It's very simple, right? So all the things would be updated in this manner, right? Now this, if this thought process is very clear, now you would take over or you can understand any kind of network, whatever comes in your future, right? Everything happens down the line in this the same manner, my dear. The complex से complex जितना भी network आप पढ़ोगे आज की तारीख के बाद, whether it is transformers, everything, so they do, everything happens somewhere in this fashion. So what is the best point over here is how the error get propagated, back propagated. That is the most important factor, right? Got this? I've taken one simple example just to give you a little bit of thought process in terms of how the things happening. Like these are the values. So what I did is, what should happen? Can anyone tell me? If I suppose this is, say, suppose I'll call it Z1 or whatever, I know, and Z2 or whatever I can call it. What should happen first? What should be done first? Anyone? And suppose this is target. Suppose this is output Y. What would happen first? Anyone?
Calculation of Z1, Z2.
Yes, first we would calculate Z1, Z2. Everyone knows the formula. Z1 is what? 0.35 into zero point 0.1
Point
plus
one, point
zero
eight.
point 0.9 into zero point 0.8, right? And then whatever activation function I would apply, simple, say for example, I'm applying sigmoid function. So some calculation would happen, right? So see, so I'm not expecting you to do all those calculations, but these calculations happening, and I'm calculating the total outputs, right? So what I did is I calculated these total output directly. So final output neuron. So what I did is Z1, Z2, and then uh, just to save the energy, the total output was 0.69, for example, right? And there, what I did is I took the target value. I took this a target value I wanted to achieve, suppose zero point 0.5. It is just number game, just to explain it. And after calculating Z1, Z2, then similarly Y, what I got is, say for example, 0.69. Understood or not? Those who are have been very regular, they would be able to understand it. So very simple calculation. For example, I got
Yes, sir.
0.69. This is suppose after applying sigmoid and all those, right? Now thing is error calculation. So what I did is, see, I did an error calculation. So 0.69, 0.5, 0.69, 0.5 का difference लिया मैंने. And then if you remember, there was a term called what? What was the term? You see, output alpha into 1 minus of output. You got this? What was the output? What was the output at here? What is the output? Output is what? I just got 0.69. So 1 minus of 0.69 and 0.69. You got this. So nothing very rocket science. So I just applied everything in terms of what I explained you, formula. So I got error at alpha is suppose this one, for example, right? And here for simplicity, I had only what? Single neuron for simplicity, right? So then I calculated new weights. What are the new weights? zero point 0.3 and zero point 0.9 should get updated first. So I updated these zero point 0.3 and zero point 0.9, and these are the new values I got it. You're getting my point. I'm not explaining, obviously, I've explained the formula. And then what should I have done? What is the next stage? I would have calculated new values of Z1, Z2 in terms of error. Yes or no? So I would have calculated these value at the hidden layers, you see. So, I mean, obviously these are numbers, so everything is getting whatever we're getting. I have not thought about it. So I got the new values of Z1, Z2. I have called it, so suppose alpha 1, del 1, whatever it is called, right? Then what I did is the new hidden layer weights. I mean, these weights got updated, right? The formula I've used is same thing, right? I've calculated these. I'm just giving you the entire approach. So old error was, suppose 0.19 after subtracting 0.69 minus of this zero point 0.5, and the new error which came out to be, for example, is after calculating everything is suppose this, right? Therefore the error is reduced. I have not explained you the all the calculations and everything. I've just gave you thought process over here, right? Because the calculations would be little lengthier. So the idea is that loss would get decreased one by one, right? This is a more typical example, a real working example, right? You have to first do H1, H2, then you would do O1, O2, all simple calculations, right? Forward fires. See, you see, I did net H1, that means net input. I mean, first I have to calculate the H1, then apply the function. You see, I did this, and then I applied the what is sigmoid function. So I got this value, right? Then what I did is I calculate the output of H2 also. So you should be able to follow this in a very streamlined manner, not a difficulty, right? Because no one would explain you the in depth of this back propagation this manner. So I thought that you should get the entire thought process. Now, the only thing that you need to understand is from where I got these all formulas. These are not anything which came out suddenly, right? So I would explain that part also, right? So if you follow these are all calculations now, you would be able to get it. Now, what I wanted to explain you that how do we get that formula? What's the time? Can we do it? Can you give me some time now? Anyone? What's the time? We still have some time?
Only 5 minutes, sir. Will it be possible to
Okay,
do it in next session?
okay. Okay, then we'll do it in the next session because this is, I mean, this would apply you good amount of brain, right? Because you have to be very, very careful. I mean, I want to explain this, right? How the back propagation is happening, right? You see, how the total error gets back propagated. And I wanted to explain this, right? If you can give me 15 minutes, I can explain. At least it would require 15 minutes. Otherwise, let's do it in the next session with a fresh mind. Okay, good. Tell me. I'm ready to do that. Whatever.
Yeah, better for the next session, sir, with the fresh mind.
Okay, good enough.
Meanwhile,
Yeah,
we'll
okay,
recap all of
okay,
the.
good.
Yeah.
Okay, you do a recap of what I and all you would find this into that particular folder. I'll put everything. Okay, because this is
Thank
the most important task. If you're going to understand this, the everything which is happening beyond this is all based on these kind of formulas only, and it can get complex also. Yes, Nikhil, you want to learn something? Yeah.
So I just need to know that where I can find these PDF and other stuff for like revision
So
and all.
yeah, so I told you you should go back over here. You can go to my folder, and there is something called shared, right?
Okay.
And here you would see all the sessions. And these are recordings, and these are the sessions. So session 3, I'll create a session 4 also, right? So you will get everything over
Okay.
here. Okay.
Okay. Okay. Thank you.
Yeah. So thank you, everyone. We'll
Sir,
meet in the next.
yeah,
Yeah.
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 So,
Tell me.
if you go back to the slides, so we started
Just
with
one.
the concept of feed forward, okay? But
Yeah.
we covered the back propagation. So, like,
Mm-hmm.
once we propagate the errors back, then we have
Mm-hmm.
to again feed it forward. Is it?
Yeah, obviously, it is a iteration. No? I've just
Yeah,
shown one cycle.
yeah, yeah,
Obviously,
yeah,
with ultimately idea is what? To reduce that error. That is what
yeah.
we have
So,
been doing. But
yeah, yeah.
yeah,
So back propagation becomes an like integral part for feed forward networks.
obviously. And this
Yeah.
happens everywhere what we did till now. It was only this only. Although it is at a very low computations because we didn't have too many neurons. But now,
Mhm.
since we would have having too many neurons, this complexity would increase, right? So I just wanted to explain you because loss function, all those, it was okay, but no one would tell you that how exactly things were happening, how this error got distributed and all those. So that is important, that must set in your mind. Okay.
Yeah.
So that
Yeah.
is the idea. Okay. So good enough. So I'll put everything there, and let me stop
And the
recording.
activation function at like for example, let's
Yeah.
say A or B.